Hello students, Jai Swaminarayan. My name is Professor Urvish Mewada. I am HOD Electrical Department, Sri Swaminarayan Institute of Technology, Gandhinagar. I am the subject matter of Interconnected Power System, which is in the 7th semester Electrical Engineering, and GTU subject code of the subject is 2170901. Students, in chapter number 2 till today, we discussed the Z-bus algorithm and the examples related to the formation of the Z-bus algorithm. Now, this is our lecture number 5 for unit number 2, and our today's topic is bus admittance matrix direct inspection method. Now let us discuss how can we format the bus admittance matrix, also how we perform the direct inspection method. Now, uh, in this diagram, you can see that equivalent admittance network and calculation of Y bus bus admittance matrix by DIM means direct inspection method. Now here consider say 4 bus network as shown in the diagram. This diagram A, uh, this G1, G2, G3 and G4 are the generators of respective bus. So this is the bus number 1. This is G2, that's why this is the bus number 2. Similarly G3 bus number 3 and G4 bus number 4. Now uh, this bus which is interconnected, these buses are interconnected to each other with the help of links. So at the bus number 1, this is the link 1, and this is the SG2 means generator to link to this is the link which is connected between G1 and G2. Now this is the 3 generator 3, that's why this is the link which is connected with the generator bus means bus number 3. This is SL4, this is again a link, and this is a link between bus number 2 and 4. So uh, this is the interconnection between each and every generating stations. So means there is interconnection between bus number 1 to 2, and with the means if you consider this link, then we can say generator number means generator 1 and generator 2 both are interconnected, and there is a relation between say bus number 1 and bus number 2 means both are connected. Similarly bus number 1 and 3 are connected, but bus number 1 and 4 are not connected. You can see there is no link between 1 and 4. Similarly bus number 2, for bus number 2 is connected with the 1, and this bus number 2 is again over here. You can see this is the link, it is connected with the bus number 3, and bus number 2 is connected with the bus number 4 with the help of link. So to have the connection with all the buses, now over here you can see the number 3 is connected with the 4, number 2 and number 1. Similarly bus number 4 which is connected with the 3 and 2, there is no connection between 4 and 1. So let us discuss how to solve this equivalent admittance matrix. Let SG1 is the this is the SG1. SG1 is the three-phase complex generator power, means it is an apparent power of particular bus, means generating station 1, S1 as bus 1, and SG2 similarly complex generator power flowing in bus number 2. So these are the means like apparent powers of respective bus to link. So this is the generating station SG1 2 3 and 4. We have 4 generating stations, so that's why this is the complex power, or we can say apparent power of respective bus respective buses. Means at the generating station 1 it is SG1, similarly at the generating station 2 it is SG2, it is 3 at SG3, at 4 it is SG4. Now let us consider the apparent power of the links. So SL1 means it's a line or link at say three phase complex power, complex and complex load power flowing uh, out of the bus number 1. So this is the say this is the load, or we can say over through this the we can say we can give the power to the consumer. So this is the SL1 means load 1, and line 1 SL2, it is say load power flowing out of the bus number 2, and SL3 is the three phase complex power of the power flowing out of the bus number 3. This is SL3, and SL4 is the three phase complex power, three phase complex means load power flowing out from the bus number 4. Now we have the equation of say SI means it is say ith number of buses. So it is SGI plus S means nth number of say complex power is SGI plus SLI. We have the generating station or generating buses, and the lines which are going out from the buses. So that's why SGI plus SLI. Now means SGI is the combination of generation and means load. So power which is generated and power which is at the load means active power which is transferring means generating at the load, and power which is delivering at the load. So PGI minus PLI for the ith number of buses plus J. This is the reactive power of you see for SGI we can write PGI plus JQGI because it is an apparent power, but here we means put together all the active and reactive powers. So that's why PGI minus PLI, because this is generating station and this is the load. So PGI minus PLI, so we can say this is the actual apparent power, and this is the QGI minus QLI. So therefore this will become SI is equal to PI plus JQI for the ith number of bus. This is active power and this is the reactive power of the this equivalent means like this is the net for this 4 bus network. Now we have drawn all the links with its impedances and its reactances, and we considered the line to ground capacitance with each other. So that's why this is the equivalent circuit of the previous diagram. So all the links and all the branches means were considered as a R plus JX, that we all know these are the transmission line. That's why we can indicate it as a R plus JX. So this is the resistance of the particular line and this is the reactance of the line. Now this is the we can say sending end to receiving end ground potential which is considered, means capacitance which is considered. So line to ground capacitance which actually imaginarily form at the we can say transmission line. So here we drawn the with the help of capacitor. So the voltage of generating station 1 is V1, similarly for G2 it is V2, and G3 it is V3, and G4 it is V4, and the current for respective buses is say for bus number 1 it is I1 for bus number 2 it is I2, for bus number 3 it is I3, and bus number 4 it is I4. Now this is the equivalent circuit of the network. So let us consider all discuss all the elements of this equivalent circuit. So let I1, I2, I3 and I4 denotes the current flowing into the bus. So these are the currents which are flowing into the bus, and the equivalent circuit of the figure above has been redrawn as below. So let us consider again. So in this we have drawn all the links between say nodes means which forms with which which forms between each bus sorry each generating stations. So this is the modified equivalent circuits where all the sources have been connected to a common reference ground. So you can see over here all the voltage sources V1, V2, V3 and V4 means negative terminal of all the voltage sources are connected at the same potential, say ground, and rest of the terminals say indicated as, suppose this is 1 and between 1 to ground potential 0, the admittance is Y10, and from V1 the current is passing, that is I1, which is going towards the node number 1. Similarly between 1 to 2 we have the admittance, that is admittance is the reciprocal of the impedance. So this is R plus jx and y12 is indicated as 1 upon R plus jx. So this is the admittance of admittance between node 1 and 2. So this is y12. Similarly node 1 and 3 it is y13, and node 3 and 2 it is y23, and 3 and 4 is y34. Similarly 2 and 4 is y24. So and the capacitance which form from the node to ground, that is at from node number 3 to ground is y30, and means this is the capacitive susceptance. So so that is why y1 y40 it is from 4 to 0, and 2 to 0 it is y20. Now let us solve this modified equivalent circuit. First of all what we need to do is we need to apply the KCL at different nodes. So let us consider how to solve this. So here we are applying the KCL at node number 1. So the current of the node number 1 is I1. So I is equal to V into Y, because Z is equal to V upon I, so Y is equal to I by V. So consider this, because Z is the impedance is equal to, suppose we write the equation in terms of V and I, so Z is equal to V upon I, and in this Y is equal to I by V. So that's why we are applying the KCL, Kirchhoff's current law. So I is equal to, for this particular line it is V1 into y10. So this is the impedance admittance of this particular 1 to 0 node, and between say 1 and 2 we have the admittance, it is y12, and voltage between 1 and 2 will be V1 minus V2, and there is a link between 1 and 3, that's why it is V1 minus V3. Voltage between node 1 and node 2 is V1 minus V3, and admittance of this line is y13. Similarly, applying the KCL at node number 2, so node number 2 is connected with the bus number 1 3, sorry, node number 2 have the relation with node number 1 3 4. So let us consider. So first of all y2, so its own impedance, so it is V2 into its own admittance, so it is V2 into y20. Now 2 to 1 it is we are considering from this to this, so that's why 2 minus 1, so that is why V2 minus V1 of this particular node, and the admittance is y12. Similarly for 2 to 3 it is we are starting from this side, so V2 minus V3 is equal to y23, and this is the node at which we are applying the KCL, that is V2 minus V4 is equal to into y24. So similarly apply the KCL at different nodes. So at node number 3, this is the equation, this is how means try to form it by your way by taking reference of these two nodes. So applying KCL at node number 4, so that will this is the equation for the node number 4. Now from these equations we can form the matrix. So rearranging these equations, and we are rewriting this in the matrix form that we get. So I is equal to, we need this form in V into Y, so this is the V and this is the Y. Now at I1, we have the admittances y10 plus y12 plus y13. So we have three admittances at say I1, the y this is the y1, this is y12. So here this is the means we are considering the rest of the elements, means of the diagonal, means except diagonal, it is minus. So minus y12, then minus y13, and y14, there is no link between 1 and 4, that's why it is 0. Similarly y12, so y for I2, y12 is minus y12, and the diagonal matrix is y20 plus y12 plus y23 plus y24. So these are the admittances of this node number 2. So we consider all the diagonal matrix, diagonal elements of the matrix is positive, and rest of the elements we consider, if there is a link, then it is considered as a minus. If there is no link, then it is considered as a 0. So similarly for I3, it is y30 plus y13 plus y23 plus y34, and for I4 it is y40 plus y24 plus y34, and voltages of this particular respective nodes is v1, v2, v3, and 4 v4. So this is how we can form the equivalent circuit of any network in terms of its admittance and its node voltage. So the admittance matrix become y11, y12, y13, y14, because we have the four nodes, that's why we consider 4 by 4 matrix. So this is the say admittance matrix of particular network. So here we have the four nodes, that's why we have till y44. So an admittance of node itself, it is y44. So where the self admittance say yii, so if we want to find out y1, y11, y22, y33, and y44, so we have the formula from this previous diagonal matrix. So this is the diagonal matrix. From that we written the formula. Suppose y11, so y11 is equal to y10 plus y12 plus y13. Similarly y44, it is y40 plus y24 plus y34. So these are the formulas. And mutual admittances means between, this is the node itself, and this is the between the means bus and link. So y12 is equal to y21, we can write this, and the admittance is minus y12. Then y13, it is y31, both are same, and it is indicated as minus 1 y13. Now y14, there is no link between y14, that is it is 0. So 23, it is minus y23, y24, it is minus y24, and y24 it is y34, it is minus y34. This is the printing mistake. So from the above equation, it is written as basically I is equal to Vy. So this is the equation, this is the formula for the Y bus, sorry, admittance, as we know that Y is equal to I by V. So from that this is the bus, means matrix of say currents of respective means branches, so sorry, buses. So this is forming one say matrix, so that's why this is called I bus. Similarly this is forming this admittance is forming one matrix, that is by Y bus, and this is the V bus. So node current matrix, this is the bus admittance matrix, and this is the node voltage matrix of respective network. Now general equation for n bus network based on Kirchhoff's current law and admittance form is basically I is equal to Y bus into V. So this is how we can write the equation for say admittance, equivalent admittance circuit of any given network. Now the general equation for the n bus is say I is equal to V bus into I bus, sorry, Y bus into V. So where I is the n bus current matrix, and V is the N bus voltage matrix, and Y bus is called the bus admittance matrix, because we consider this formula for the nth number of say buses and links. So I is equal to Y bus into V, so Y bus is our Y11, Y12 to Y1n, because we have nth number of links which are connected with this with bus number 1 or node number 1. So similarly we can write the equation y21, y22 and y2n. So this 1 2 will become n, so that's why yn1, and this 1 2 will become n, so this will become ynn. So this all are the y11, y22 and ynn are the elements of say admittances of diagonal matrix. So and it is called the bus admittance matrix, and V and I are the n element node voltage matrix, and node current matrix, and node current matrix respectively. uh, this is the subtopic of this theory. So steps for formation of Y bus by inspection method. So let us consider steps for the inspection method. uh, so these are the steps that we followed in the previous theory. So it is written in the terms of steps. So first is make equivalent circuit from the given single line diagram, so that we form from the single line diagram we form equivalent circuit having equal say potential of means voltage sources which are connected at the equal potential, and rest of the elements which are connected with its impedance links. So impedance or admittance links. And step number 2, then observe the dimension of the matrix, say Y bus. Means if we have 4 number of buses, then the Y bus will be 4 by 4 matrix, and say n is the number of buses, so x is equal to n plus 1, so n plus 1 is equal to 4 plus 1 is equal to total number of nodes. We have the number of nodes is 4, because one additional node at we create the ground potential of say all the voltage sources. So that's why number of nodes will become n plus 1. So the self admittances of node m is say y means sorry is the sum of the all admittances of elements, so it is connected to the node. So that's why in the equivalent y is diagonal element. So we consider it is from p means p is equal to 0, means we are starting from the say bus number 1 to nth number of bus, and for that it's having its own say admittance. So ymp, where m and p both are not equal, so y11 is equal to all means summation of all the elements connected to the node 1 and 2. So this shows that we derived in the diagonal matrix, that if you recall that y11 is equal to the addition of all the admittances which have the links or connection at the node number 1. So why suppose we write we write this suppose formula for the y11. So it is summation of all the elements which are connected at node number 1 and 2. Similarly, mutual admittances means between links, so ymp, so off diagonal element, these are the diagonal element and this is the off diagonal. So as we know that off diagonal elements elements is are say indicated as minus. So ypm ypm is indicated as minus ymp. So suppose we write for y12, then it is minus means summation of all the elements which are connected between node number 1 and 2, sorry no, between node number 1 and node number 2, or bus number 1 and bus number 2 respectively. So this is the second number step. And consider a bus admittance matrix y bus is equal to n cross n, because we have the say suppose 4 nodes, then 4 by 4 matrix is there. So the matrix can be described as y bus n cross n, that means it is y m m to YPP, means this is the diagonal matrix and this is the off diagonal matrix. So YM will become M to P is the connection, and this is the M, that's why YPM, and over here M will become P over here also. So YM and this will become YPP. So this is the diagonal matrix. Suppose we have the four nodes, that means Y11, Y22, Y33, Y44, and rest of the links which are connected is called off diagonal elements of the admittance matrix. So that is indicated as a minus. So this is how we can form the Y bus for sorry, n cross n, means if number of nodes are 4, then this will be 4 by 4 matrix. Now if some elements is added in this network, then the entries of the existing bus admittance matrix Y bus will also affected. So the location of the element which signifies the extent of the modification. Let us consider the modification of means two cases. So um, let us start the case number 1. Consider an element having admittance say YMP connected between bus M and P. Due to this four entities, the in Y bus matrix get affected when can modify this and entries. So YMM new is equal to YMM old plus YMP, and YMP new. So this is the off diagonal, so YMP old minus YMP. Similarly, YPM new is the YPM old minus YMP, and YPP new is equal to YPP old minus YMP. So these are the formula from which we can determine the admittance matrix. So thus we add the elements one by one and modified the entries of Y bus, and the equations are these are the equations which shows the how the new bus admittance matrix can be formed from the given network. So this is the case number 2. So over here it is considered the new element is connected from the mth bus to the reference on ground. So for this case only entry YMM will be affected because it is connected only from M to ground. So in this case it is connected with all the links which are present in the means all the buses which are present in the network, and in this case it is only connected with a node which is connected to the ground potential. So let us consider how it will be. So YMM new is equal to YMM old plus YMM, so new admittance matrix by adding that link. So YMM is the new element connected from mth bus to the ground. So advantages of the bus admittance matrix, it is discussed over here. So the first advantage is preparation of data is simple and reliable, so we can easily solve any network using bus admittance matrix. It is easy to format and modify the Y bus matrix, because if we have an addition of the say links and removal of the links from the network, so we can perform it by as we discuss in this theory, we can add or subtract the links as per our requirement, means admittances of all the links as per our requirement using the formula which we seen in the theory. So the bus admittance matrix is a sparse matrix. What is sparse matrix? Most of its elements are zero, because thus the memory required by the computer is less, because rest of the elements are zero means except the diagonal matrix. So for large power system networks, more than 90% of its off diagonal elements are 0. So if they are 90% means they are 0, so it requires less memory to store this data into the computer or for the iteration, means solution. And this is the important question, why bus matrix admittance matrix is a sparse matrix. So in generally admittance matrix, each non-zero of diagonal elements corresponding to the network branch connecting to the pair of the buses by the row and column of the element. So generally in interconnected power system, most transmission networks exhibits the irregular in their connection arrangement. So majority of the off diagonal elements are 0. So the admittance matrix which are formed are relatively sparse. To be a sparse matrix, the following advantages, like the storage requirements are small, and the direct solution using triangular technique can be obtained much faster, and round errors are very much reduced. So this is how we can say that any admittance matrix is a bus admittance matrix is a sparse matrix, because we already discussed that around 90% of its say admittances which are connected to which are not connected or connected between each of the links say is 0. So that's why it is called the sparse matrix. So let us consider the Z bus matrix from the Y bus. So we had the equation in previous theory, that is Y is equal to I by V. Now in this, Z is equal to V upon I. So the network model is simplified as analyzed by the equation. So the equations are formed through matrices, the admittance matrix Y bus and impedance matrix Z bus, and the current matrix is I and voltage matrix is V. So this is the voltage matrix, this is the current matrix, and this is the impedance matrix, sorry, admittance matrix. Sorry, Z is the impedance, so impedance matrix, and this is the Y. So it is called the admittance matrix. So this is how we can write the for equation for the Z and Y bus. So not here we have the one notation, that is admittance matrix is the inverse of impedance matrix and vice versa. So Y inverse will be the Z, and Y is equal to will become the Z inverse. So Z is equal to R plus JX. So this is how we can find out the Y bus algorithm, and we can form the Y bus and Z bus matrix. uh, After this theory, you have the worksheet question. The first question is why the incidence matrix is a sparse matrix. This is the most MP question. And the assignment question after this topic is explain the equivalent admittance network and calculation of Y bus with suitable diagram and expression. Also, and list the advantages and advantages of bus admittance matrix Y bus. So related instructions which are written below the assignment question and worksheet questions. So please read it carefully. You can take the snap of this, and if you have any query or any doubt, then we can solve your query and doubt in our doubt solving session. Also feel free to call me, you have my number. So thank you very much, student. Jai Swaminarayan.